All right. So this is going to be for anybody that was absent yesterday, yesterday being Wednesday, or if you're having trouble understanding this new concept of resistors in series and how we're approaching our circuit problems now. So up until now, we've been using Ohm's law to calculate unknown variables, whether that be voltage, current, or resistance. And we've kept it pretty simple. You've been given, like a single resistor or just a setup where you're given two out of the three pieces of information you need in order to use Ohm's law. And that's going to still be the case in these problems. It's just not going to always be the case from the beginning. So, what we started doing yesterday is calculating total resistance in a circuit just based on the resistors that are present, not using the voltage, not using the current to help us with that. And the way we started this was by looking at resistors in series. Now, remember, series is where electricity is flowing on one pathway, okay? And the way we solve resistance in series is a direct result of electricity flowing on that one pathway. And when we look at this formula up here, hopefully you'll understand that a little bit better. Now, before we can start with these problems, because I know when you see this over here, that looks like a lot to do. Um, in actuality, it's not. Okay, once you get past the initial hurdles of what am I trying to solve here, it's pretty easy. You're going to be referring back to Ohm's law a lot and doing those calculations that you've become really good at. So, something we've got to be reminded of before we start when we are talking about resistors in series, it is vitally important that we remember our rules for series circuits because these dictate how we approach this. Okay. Now, if you go back, like, a couple of weeks ago when we started talking about this, in a series circuit and only in a series circuit, parallel is another story, voltage is going to be shared in here. So the voltage that my battery is providing is going to be shared amongst the resistors that are in the circuit. In other words, it's going to be split up somehow. Up to this point, like for example, we would have a circuit, and if I said we have a 9-volt battery and we have three light bulbs in there, and I would ask you how many volts each light bulb would get. Back then, I wasn't telling you how many ohms of resistance each light bulb was. All we cared about was that I had 9 volts and I had, again, like three bulbs. And you guys would rightly say, well, each bulb gets 3 volts because the voltage is split up, it shares its voltage. And that's true. But in reality, in life, we typically don't have identical resistors throughout the entire circuit. There's going to be resistors of different values, and those different values mean that they're going to need different amounts of voltage. That voltage isn't always going to be split up evenly. So that's kind of what's new for us today. But by remembering that voltage is shared, that's going to help you get to the correct answers for these problems. Now, the second thing, and also incredibly important, is to remember how current behaves in a series circuit. So remember, current is constant everywhere in the circuit. That means wherever I go in my circuit here, my current's going to be the same. And what I was saying yesterday, and I'm going to continue to harp on it, is that if you know the current anywhere in a series circuit, then you essentially know, well, actually, not even essentially, then you know the current everywhere. And the reason being is because this is series. Or in simpler terms, the reason is because this is a single pathway for electricity to flow. And if you think about it, if I have electron after electron passing through this circuit, they all have to be moving at the same speed. You can't have something in a single file line where parts of it are moving faster than others. It just doesn't work that way. Okay? Now, we'll come up here to our formula in a second, but I do want you to keep in the back of your mind when you're thinking about current, think about it as the way we think about, like, not the speed limit, but like how fast a car is going. If you're going 65 miles an hour in a car, you're going 65 miles an hour in a car. Part of your car isn't going slower, and part of your car is not going faster. It's all traveling at the same speed, and that's the case here. So let's have a look, see what looks different first, so we can kind of point those things out, and then we'll solve this particular problem right here. So, first thing it's going to ask us we see here, R is something that's very familiar to you. R, I, V, you've seen all of those things. The thing that might seem a little new now is I've added this sub T here. Sub just meaning that it's below, right? Like a subscript. So RT is the same thing as R total, or my total resistance. I'm going to write the word total in here for now, just as you're learning this. So this first one is asking me to solve for my total resistance. Now, right out of the gate, this is something we haven't covered yet. But in class, I've seen it when I've snuck some of these into some of our questions leading up to this. And you guys are going on instinct, I guess. And I don't like the term common sense, but when you look at the problem, you guys understand series circuits enough, I think, to where you're getting this. If I want to know what my total resistance is in a circuit, in a series circuit, I simply need to add up all the resistors in the circuit. And if you think about it, it makes sense. I mentioned in class yesterday, when you guys go to chemistry next year, this won't help you with everything there for sure, but when you're getting into chemical reactions and trying to understand not what happened, but why it happened, if you look from the point of view of a single electron, because remember, that's all electricity is, it's flowing electrons. If I'm a little electron coming out of my battery here, what I'm doing is I'm leaving my house and I'm traveling around the block, and I eventually am trying to get back home, right? That's kind of just what it does. Now, along the way, this electron, since there's one path, has to go through everything that's in that path. So here it's going to go through 1, 2 resistors before it gets back home. So if you think about it, this electron is going through 20 ohms of resistance here and 10 ohms of resistance there. So it's going through a total of 30 ohms of resistance. So we would say that this circuit has 30 ohms of resistance. And that would be my total resistance. And that's what I'm going to put right here. Now, there is a formula for this. I know you might think there's no point. You just know add them up, and that's great. If you can remember to just add them up, that's fine. What you're doing when you add them is you are using this formula. All right? Now, what this states is that RT, or my total resistance in a circuit, is equal to the sum of all the resistors in that circuit. So if you look here, if I've got RT, or R total, equals R1 plus R2 plus R3, and so on. You can go on to infinity resistors if you wanted to. Now, when you come back to this circuit, because you see this R1, R2, R3, those little numbers, these subscript numbers, they're going to correspond with a resistor in the circuit. So you see here, this is R1, we would say resistor 1. This is R2, resistor 2, and they'll each carry their own value. These numbers are kind of a marker to help you keep track of which resistor we're looking at in the circuit. But if we took this same thing and plugged it into that, you're going to get the same answer. R1 would be 10 ohms. R2 would be 20 ohms. And this tells us to add them, which gives us 30 ohms. All right. Now, taking this thing we just figured out, combining it with some things that are already given to us, such as we've got our voltage over here, we can now do some simple calculations. We can start to calculate. You see here, we're looking for total current. We're looking for current at resistor 1, current at resistor 2, and then we'll get to the voltages at those points. And this is where we've got to be careful, okay? Now, finding total resistance, that's going to be pretty easy for you at this point, right? Remember, if I wanted to find, I said resistance, finding total current is going to be pretty easy for you at this point. So if I'm looking for total current, you come up here, remember how we use the formula finder, you cover up what you want to solve for, and the mathematical operation you need to use to get it is left behind. So in this case, voltage divided by resistance is going to give me my total current. Now I have my voltage right here at the battery. They're telling me we've got 90 volts. And this told me to divide that by my total resistance, which we just solved. There's my total resistance right there. So I'll put 30 ohms. We do that math, we get 3, and you need to think of the unit for current. That's going to be the amp. So 3 amps is my total current. And that's what I would put in here. 3 amps. Easy enough, right? That is no different than anything you've been doing. This is just like all of the Ohm's law practice we've done to this point. Okay, now though, now moving into this next one, this is where you remembering your rules, this is where that's going to come into play. Because if you don't remember these, you can make some pretty bad mistakes trying to get to this part. All right, now I'm going to show you the right way to do it first. Okay, but then what I'm going to do is show you with someone who doesn't remember these rules, the way they might approach this and why that's going to give them an incorrect answer. Okay, so the first thing we want to do, looking back to our rules. Okay, we're trying to solve for current, so let's remind ourselves of our rules for current. Current is constant everywhere in the circuit. And like I said earlier, in other words, what that means, if I know the current anywhere in this series circuit, then I know the current everywhere. All right, now, do I know the current anywhere? I absolutely do. We just figured that out. We know that our circuit has 3 amps. So if this circuit has 3 amps, guess what? It's going to be 3 amps everywhere. So for these two, I can just fill them in right now. 3 amps is going to be going through resistor 1. 3 amps is going to go through resistor 2. And if you think about it again, it makes sense. Everything in this series circuit, since there's one pathway, is traveling at the same speed. And again, think about current as how fast the electricity is flowing. So if I've calculated 3 amps in my circuit, that means everywhere I go, it's got to be 3 amps. Okay, I hope that makes sense. Now, let's look at how somebody might make a mistake here if they don't remember these rules. And I do get that because parallel and series, they're so similar in many ways, but they're polar opposites in the important parts. So it can be easy to confuse that. But just through repetition and paying attention to the problem, are we going to get through that sort of thing? So let's say I forget that rule, okay? And I'm like, all right, what is my current at resistor 1? You might go, well, that's easy. I've got my Ohm's law formula finder right here. I know my voltage is 90. I'm going to go ahead and write wrong up here just in case. So I know my voltage is 90 volts and my resistance right here is 10 ohms. So I might divide that. And then I would get 9 amps. And you might think, fine, okay, and then just move right along. But that's going to cause problems for you because 9 amps, you can't have a total current of 3 amps in your circuit and then all of a sudden have 9 amps coming from a single resistor. That would be a red flag to you, okay? If you calculated your total current already and you're getting a number that is higher than that should be a red flag. Now, let's say though that you're just powering through. It's just a homework assignment. You don't care. You're just trying to get it done, whatever the reason. Let's look at resistor number 2 and see what we would get. I'll put 9 up here for the first one we got. Apologize, phone's ringing. 1 second. Okay, let's see here. Movie magic, and we're back. All right, so where was I? All right, we had solved incorrectly our first one here. And let's say that now we're going to go ahead and try and solve this one. So again, you would just say, well, if I need current, I take my voltage and divide by resistance. So you would take your 90 volts and you would divide that by the 20 ohms of this second one. And my mental math game is weak, so I'm going to grab a calculator. Oh gosh, that's actually much easier than I thought. But you would get 4.5 amps. All right. So again, now we're looking at 3 amps total that we calculated, 9 amps for this one, which again doesn't make sense because if you have a total of 3, how could you have more? And then the same falls into place here. Okay, so again, doing this is a direct result of either not knowing or not remembering how current behaves in a series circuit. Okay, so be careful of that because the problem will let you do it. You can do the math. It's just going to come out and give you values that are not going to make sense because they're not following what we see in a series circuit. All right. So let's get back onto the right path of things. So just a quick reminder again, if you know the current anywhere in that circuit when it's series, then you know it everywhere. You don't need to recalculate it every single time. We can confirm this at the end. Once we have all of our other data, you can go in and you can confirm that, yeah, it is 3 amps everywhere. All right, so all we've got left is voltage, okay? Now we know what our battery is putting out here, but remember, it's a series circuit, so voltage is going to be shared. So this voltage is going to be split up between these two resistors. And in the past, remember, in the past, I wasn't telling you how many ohms these resistors were. We were just pretending as if they were two identical resistors. So this is where that changes. In this case, this resistor has 10 ohms of resistance. That's how much pushback it's giving against the current. This one has 20. This one has twice as much resistance as that one. So what's going to happen here is voltage is going to have to work a little harder through one of these compared to the other. Now, the one with the higher resistance is going to cause voltage to kind of push harder, if you want to think about it that way. And the reason being goes back to the fact that current is the same everywhere. If that electricity has to flow at the same speed through this circuit, when I get to an area of more resistance, I'm going to have to give more force in order to maintain that speed. Otherwise, it would slow down, right? So that's the whole idea of why some of these will get more voltage than others. So let's do our calculation. If I want to find the voltage at resistor 1, so the V1 here, that 1 corresponds to that resistor with the 1. That's what these little numbers here are for. So when I see V1, that means I'm going to come up here to resistor 1, and I want to find out the voltage right there. Now, if we look at our formula finder, if I wanted voltage, I need to know my current and I need to know my resistance, and then I'll multiply them, and that will give me my voltage. So do we know our current? We absolutely know our current. We had calculated it over here, and then based on what we understood about series rules, we knew that that would be the same here and there and everywhere else in that circuit. So my current is 3 amps. So I put my 3 amps, and I need to multiply that by my resistance right here. Now my resistance at 1 is 10 ohms. And when I do the multiplication, I get 30 volts, right? Because we are measuring for voltage. So I get 30 volts. So my voltage at resistor 1 is 30 volts. Now you see I've got a total of 90. This one is taking up 30 of that. So you might deduce really quickly in your head. You're like, well, that only leaves 60 volts left for the second one. So let's see. Let's see if that plays out like that. So the last thing we want to solve for is V2, voltage at my second resistor. So let's go ahead and do the same thing. Again, remember, if I want voltage, cover it up, I need I and R, and I'm going to multiply them. So my current at R2, again, is going to be 3 amps. And I'm going to multiply that by my resistance at R2. And here, this resistance is 20 ohms. So we'll put that up here. And being careful to put in the units. It's very important. It's easy to skip the units. But what happens is you start to get confused when it comes to your final answer. If you make mistakes, it's hard to go back and kind of see where mistakes were made if you don't have the units. Because a common thing that happens, not so much with voltage because it's multiplication, but when we get to anything where we're dividing, right? If you do that and you don't have the units, it's easy to accidentally flip voltage and resistance and get an incorrect answer. I actually did that in class yesterday. Sadly, I had the units next to them and I still did it wrong. So it happens, right? Okay. So 3 amps times 20 ohms is going to give me 60 volts. All right. So 60 volts. Kind of like we predicted, right? Now, a way you can check yourself for this. When you've calculated your voltage, if you remember again, voltage in a series circuit is shared. So this 90 volts is going to get split up in the circuit. In this case, we just have 2 resistors. If I had 10 resistors in there, it works the same way. You would find all of your individual voltages at your individual resistors. And when you're done, If you take the sum of all of those, if you take all of those resistors, all of those voltages, and add them up, they should equal the original voltage of your battery. Okay, because remember, that is just getting shared amongst all of them. So when you put them all together, they should equal what you started with. And this is the way we use, number one, resistors in series, but more importantly, the way we use our understanding of the rules of series and parallel circuits in order to solve more complex circuit problems. Now, the assignment that we did yesterday in class, I think it was 72, this is the first problem from that. So, and we did this together in class. So you can use this, and hopefully this video is helpful um, for solving these. Now, as you go through them, some will be straightforward just like this. Others are going to have you, they'll tell you R2, but they won't tell you what its resistance is. But then you'll be looking for other things. They might tell you what the current is somewhere in the voltage. And again, you'll use your understanding of Ohm's law in order to solve for all the unknown parts. The advice I can give for that particular assignment, when I set this up, the things I'm asking you for, if you try and solve them in order, you should be just fine. I set them up to where if you solve this, that might kind of be the key for solving the next part and so on. Okay, we'll be doing this for the next several days. Today is a short day, so what we're going to do is just review yesterday's assignment, and then tomorrow we're going to start with resistors in parallel, which does take a lot more effort to get through. Just going to be honest. But if we can take care of this here, okay, I added our resistors in series to this because this is a very easy concept, but the rest was kind of introducing you to how to address these problems. So if we can get this feeling pretty comfortable with this, that'll allow us to focus more on the parallel resistors. Okay. All right. So I'm always here if you have any questions. If you're at home sick, I'm sorry. I hope you feel better soon. If you were just absent, for any other reason, I hope this was helpful. And for you guys that were in class, but I know I get it. This stuff can be tricky in the beginning. I hope this was helpful as well. All right. Have a good day.